Hi, everyone. I'd like to welcome you to this TOPIQ webinar on separating multiple diffraction patterns with CrysAlisPro. I'm your co-host, Mark Del Campo, and it is my pleasure to introduce you to your host, Dr. Pierre Lemagares.
Thank you, Mark. Thank you for the nice introduction. And everybody, welcome. Thank you for attending this new Rigaku webinar here today. Today, indeed, we are going to talk about using CrysAlisPro to manually separate multiple diffraction patterns in the reciprocal space. So this is indeed in those cases where CrysAlisPro cannot really distinguish that there are several diffraction patterns and therefore leads to a wrong indexing. So sometimes you have to get in there yourself, separate the diffraction patterns or clean up the diffraction pattern yourself, and then you should be able to index just fine and go on with your data processing. So one of the examples I'm going to use today is a non-mirror-hydral twinned dataset, and that gives me the opportunity to point you to another webinar that we ran about a month ago on how to handle and process a twinned dataset, a non-mirror-hydral twinned dataset in CrysAlisPro. So that example did not necessitate any manual intervention to separate the diffraction patterns from the different components. It was a little bit more automatic, so to speak. But I would point you to that webinar that we ran about a month ago. So if you want to watch it, you can go to the Rigaku webpage, open up the support menu, and then open up the past webinars webpage. That webpage will list all the webinars that we actually ran for the past month and a half or so, and that in that list, look for that webinar. So as I just said, so these webinars are all recorded, and within the course of next week, probably now, there will be a recording of this present webinar on the Rigaku webpage as well. And the data sets I'm going to use today will be sent to you also, or a link for download them will be sent to you also at the same time that a link is sent to you for watching the recording. You are welcome to ask any question you want during the webinar. We'll do that in writing though. And so to do that, you can use the Q&A feature at the bottom of your Zoom interface. So click on the Q&A button and then write your questions. These questions will get to Mark. Mark might answer some of them during my presentation, and otherwise he will send them to me at the end of this lecture. So the two examples I'm going to use today are shown on this slide. The first example is a dataset showing heavy icing. This was an internal dataset collected by my colleague, Dr. Fraser White, who is now our single crystal product marketing manager. So what Fraser did is that in the course of the data collection, he turned off the protection shield around the cryostream. So of course that caused ice to start building up at the tip of the cryonozzle. And then by the end of the data collection, the ice had grown so much that it even encompassed the crystal. Of course, that created a lot of ice features on the diffraction images. The second example is a non-mirror-hydral twin, as shown by this view of the reciprocal space. It's a data set that was collected by one of our users, Professor Maria Gdaniek at the Adam Mickiewicz University of Poznan in Poland. So to separate diffraction patterns in CrysAlisPro, you use a tool that is called Lattice-It. So that tool is accessible from the eWorld 3D section of the Lattice Wizard. This is also where you look at your reciprocal space. And the Lattice-It tool is able to separate rows of reflections into separate groups at once. So here is an example of what can happen. So if you have such a diffraction pattern with intertwined rows of reflections, once you apply Lattice-It to that view, this is what should happen, whereby Lattice-It is able to isolate one of the two sets of rows of reflections, in this case, the vertical rows, within bars. The other set of rows, the oblique rows, are now highlighted in green, ready to be moved into a separate groups. A separate group. So now you have the two sets of rows into separate groups of reflections, and you can index them separately. So like I said, this you should be able to do that at once. All these bars are, these red vertical bars are defined at once. So there is no need to click on the individual reflections to put them in a separate reflection file. There's no need to click and drag either on top of rows of reflections. These two things would be quite time consuming and tedious, of course. The last thing is that once the bars have been created, you can slightly modify their tilt angle, the period between consecutive bars, meaning the distance here between consecutive bars, and you can also modify their width. So by modifying these three parameters, you can control exactly the reflections that you imprison within the bars, making sure that you don't that you capture the reflection from one diffraction pattern only, and not any reflection from the other diffraction pattern. So let me now minimize this view and jump right into our first example, the IC datasets. Okay, so the first thing I'm going to do is play that dataset as a movie to you, so you see what's going on during data collection. So you can browse through images of a dataset in CrysAlisPro using the buttons at the bottom left of the CrysAlisPro interface. So if I click on this button down here, the double arrow button that with arrows that point to the right, I jump to the consecutive to the next image one at a time. Okay. If I click on the next button over, I jump 10 images at a time. And again, the next button over makes me jump to the first image of the next run. So here I'm showing frame number 1 of run number 2. And again, if I click once more, now frame number 1 of run number 3, and so on and so forth. So these three buttons here are for forward motion. The equivalent 3 buttons on the left-hand side here are for backward motion. And the button in the middle allows me to play the dataset as a movie, which is what I'm doing right now. So I hope that through Zoom, you can see, okay, what was going on. I'm going to play that dataset a couple more times so that you can see that at the beginning, you see on that first diffraction image, everything is clean. There is no trace of ice feature. And again, if I play the dataset as a movie, so the data are clean for a while, then ice starts appearing, and then at the end, it becomes really bad. Let me play it once more for you. Clean. Ice starts appearing, and at the end it's really bad. Okay. Here is another way of looking at that data set. This is looking at it in the reciprocal space. So if I open the Lattice wizard from the top button here on the left-hand side panel, and then I open the eWorld Explorer. Actually, let me run the pick hunting real quick first. And then open the eWorld Explorer, and you see what's going on here. This is, we have actually a lot of, we have a pattern of crystal reflections coinciding here with the lattice points. And on top of that, we have a whole lot of ice features randomly spread throughout the reciprocal space. So there's a nice feature in CrysAlisPro that allows you to look at your data set on a per scan basis. So expand the filters tab on the right-hand side panel, and then enable the run feature here. So this is the feature that allows to display the whole data set scan by scan. So typically I would click on none to remove everything from the display. And then I would bring back into the display scan number 1 only by checking that box for scan number 1. Okay. If I zoom in a little bit with my right mouse here, you see that all the reflections coincide with the lattice points, and then everything is clean. There's no sign of icing at all. Same goes for scan number 2 and 3 and 4 and 5. And up to scan number 5, everything is clean, and that's true along A star, B star, and C star. If I display now scan number 6, some ice features start appearing, but it's pretty light. 7 is pretty okay also. And 8, it starts getting a little bit worse. 9 a bit worse, and so on and so forth. And now as I bring more and more scans into the display, then the ice feature appears worse and worse and worse. Okay, so remember that the run feature in the filters tab that allows you to see the evolution of your data during data collection, so you can check as to whether something went wrong during data collection or not. And here I can tell that almost half of my data set is just fine and clean. The other thing I want to show here is that you see the structure that you see here on the right hand side was obtained via automatic analysis of that data set. That means automatic processing, automatic indexing, automatic processing, and automatic structure solution. So CrysAlisPro does actually a really good job with this very high icy data set because there are enough crystal reflections that can be distinguished in this case from the ice features. So the reason of me choosing the data set is just for the sake of this webinar. I needed an example of an icy data set. Even though CrysAlisPro does a good job by itself, I'm still using this data set here today for the sake of my demonstration. Okay. So you see that automatically, though CrysAlisPro got a pretty nice feature structure here at about 6% of R1. The R-int was about 7%. So all that for this dirty data set with ice features, this is not too bad. Okay. So now let me jump to another instance of CrysAlisPro for that same data set, where basically I gathered the data only from the dirty scans though. Okay, so to show you what I did, this is the Lattice Wizard interface that is already open here. From the pick hunting feature, I click on the little arrow button to have access to more advanced options. And I select here, pick hunting with user settings. And this is only to show you that the first data that I gathered here were from scan number 9, which, if I remember what I showed you in the reciprocal space before, it's one of the first scans that is really dirty. Okay, so the first 8 scans were discarded from pig hunting. So basically, the cleanest data, I didn't use it. I'm just using the dirtiest part of the data set here. And as a result, when I did that, I already ran indexing, and you see here that the indexing is kind of bogus. I've got a long unit cell axis of 145 angstroms and only 4% of the reflections indexed. The correct unit cell parameters, if I go back to the previous example, are 9, 11, 29. Whereas here, by gathering the data from the dirty scans only, I've got the bogus set of unit cell parameters of 15, 40, 145, and 32. So obviously something is wrong, and that's when you want to go to the reciprocal space to see if you can fix things. Okay? So this is what the lattice looks like at the moment. The lattice that you see here. But of course, we've got very little reflections here. The program basically missed the location of the crystal reflections. You can see that on the intensity histogram on the right-hand side here, along A star, B star, and C star, very weak reflections, or along B star, there's actually even nothing there. So if I make these lattice points appear, the red, green, and blue boxes, these materialize the position of the lattice points, and you see that at the lattice points, there's weak or no reflections at all. So that's because our unit cell is wrong. So the game for me now is gonna be to rotate around this diffraction pattern until I see rows of reflections bathed basically in that sea of ice features. So to do that, I will left click on the view here and rotate around until I see rows of reflections. And if I see rows of reflections, I know that this will be the part of the diffraction coming from the crystal, and then I will apply the Lattice-It feature to that to those rows of reflections. So basically, with the left mouse here, I click and drag, and then slowly and rotate slowly to see rows of reflections. So you see up here, there, I can see some rows already. They might not be too obvious, so I'm going to rotate some more. Here is another orientation where I've got rows here also, okay? And if I keep rotating, in this case, I'm rotating in the horizontal direction. I just chose that direction as such. Do I have something more here? There, I've got another orientation that shows me these nice rows of reflections also. Okay, so I'm trying to align them as well as possible here with my left mouse again, and that's about the best I can do here. So I'm getting ready to apply the Lattice feature to those rows. We're going to take our first break of the day so that Mark can ask you the first poll questions that we had scheduled for today. Just a little poll for to submit to you guys, if you don't mind asking this question that Mark is about to ask you now. Go ahead, Mark.
Thank you, Pierre. Okay, so the first poll question is, how many of your crystals would you say are too weak to analyze on your local sealed tube system? Less than 10%, between 10 and 20%, or more than 20%? And I'll give you all a few moments just to make sure everyone has a chance to select an answer. Got about 66% of people voting, almost 70%. So we got a good response for this poll. So voting, I'll let this go up to about a minute of time and then we'll cut it off. 10 seconds. And we'll stop the poll here. So it looks like the majority of people have crystals that are too weak in the 10 to 20% range.
Yeah.
Thank you.
You can share those results also with everybody, I suppose, Mark. Yep. So there are still a quarter of you who said that more than 20% are too weak to be analyzed on a seal tube. And so there's going to be a couple more poll questions coming your way before the end of this webinar that are kind of a follow-up of that question in those cases that you have weak crystals. All right, back to work here for with our IC datasets. So now to apply Lattice-It to those rows of reflections I just determined before, I'm now going to the Lattice-It tab on the right-hand side panel at the bottom. And I click on it to expand it. And I enable the Lattice-It feature by clicking or by checking the box in front of it. Okay, this little box here, I click on it. And now as soon as I do that, I've got now these vertical lines, those two vertical lines attached to my cursor, and they follow whatever I do with my cursor, so I can orient them as I wish and bring them at any location I wish on the screen. So the game here for me is to align one of those lines with a row of reflections as well as I can on top of it. And once I'm there, if I'm lucky, CrysAlisPro will hopefully see the same rows as my eyes see. So you see here, I'm pointing CrysAlisPro to those rows of reflections that my eyes see. Now, at this point, nothing is set in stone yet, because if I move my cursor, then the orientation of those lines changes, and then everything is broken. Okay, so let me do that again. Align my cursor with one of those rows, and now I'm going to freeze up the view by clicking once more on the left mouse. And now you remember the view that I showed you in one of my slides previously, whereby red bars have been drawn on top of rows of reflections, and whatever reflections have been left outside of those rows are now highlighted in green, ready to be moved to a different groups. And that's all needs to be done. This is how Lattice-It works. So one thing here is that I can maybe make those red rows or red bars a bit thinner, just to get rid of a few more reflections coming from ice. And to do that, I can use the width option on the right hand side panel here, and use these two little arrow button, left to make the width lower or smaller, and right to make the width larger. So here, if I click on the left arrow button, I make the rows a little bit thinner. Okay, and I'm gonna stop here, and then click on the button that says Move Selected To. That will move all the green reflections to a different group. In this case, group number 2. You can choose either any group you wish here. So I'll click on Move Selected To. Here are a bunch of reflections that were moved into group 2, as shown in the table at the bottom right. Then I uncheck this box in front of number 2 to remove the group number 2 from the display. And I disable the Lattice-It feature by clicking on None, on the None option. So that's what I've got here at the moment. So it's obviously already a much cleaner diffraction pattern. So now I'm going to rotate that diffraction pattern again to try to find another orientation where I see another set of rows. So here I choose again any direction I wish, and I rotate the diffraction pattern a little bit in the horizontal direction until I find this other set of rows. And then again, I can see that there is a set of rows with lots of reflections in between them. So this is another good orientation to apply Lattice-It to and clean up some more rogue reflections here, those that are placed in between the rows of reflections. So again, I push or check the box in front of the Lattice-It option, align my cursor with one of those rows of reflections. CrysAlisPro again sees what I see. I click once more on the left mouse, and I've got now a second batch of green reflections ready to be moved again to different groups. And here I can move that second batch of reflections into the same group or a different group. It doesn't matter. These reflections coming from ice are just junk anyway, if I may say so. So you don't care in which group you push them to. So anyway, I push the button Move Selected To, remove everything that is in group number 2 now from the display, and then disable the Lattice-It feature once more by clicking on None. And that's the diffraction pattern I'm left with now. So you see something that is much cleaner. Okay. So now I need to try and index the reflections that remain and see if I can get a better indexing. So typically I would get out of the reciprocal space viewer now, okay, and clean up the reflection file. The thing is that so far I've cleaned up the display, but those green reflections are still in the reflection file. The thing is though that once I've put them in a different group, they have now attached to them a flag, okay? And I will use this flag to delete all those flagged reflections basically. So to do that, I click on the little arrow button that is beside the main button for the eWorld Explorer. So I click on that little arrow button to have access to more advanced features. And then I select the second option that says Peak Table Flags. And in the dialog that opens up, I go down to the bottom of the list and select Delete Skip. I will delete, by doing that, I will delete all the reflections that have a flag skip assigned to them. So I click on it. CrysAlisPro asks me whether I really know what I'm doing here. So yes. And then now I can certainly run indexing again. And now I'm back to my 9, 11, 29 unit cell parameters. And I've got 80% of the reflections indexed. So you can certainly push the button Refine Instrument Model to see if you can improve that a little bit, but in this case, nothing happens. A good practice though is to go back to the eWorld Explorer to now have a look at what the reciprocal space looks like within that new lattice. Okay, so I will go to the top of the interface here and click on that button that shows a lattice to bring the lattice itself back into the display. And I will show the whole diffraction along the reciprocal space axis here, along A star, B star, and C star, okay? So if I zoom in a little bit, see that along C star, everything is beautiful. Along B star and A star, there might still be some cleaning that could be done, but you see that the majority of the reflections do coincide with the lattice points. If I left click on the lattice link here and say refine unit cell just to bring about the display of the lattice points here on the intensity histogram along A star, B star, and C star, and here I'm talking about the red, green, and blue boxes. If those boxes don't appear, left click on the lattice blue lattice link here and say refine unit cell, and they will appear. So you see that now we've got strong and sharp reflections within the boxes representing the lattice points. So that means that the centroid of these reflections are exactly where the program expects them to be. So basically with these unit cell parameters now, we're basically hitting the reflections on the head, or hitting the nail on the head, okay? Okay, and so that's how you clean up a diffraction pattern from indexing. So at this point, although my indexing was wrong when gathering data from these dirty scans, I could now go on with data reduction because I've got the proper unit cell parameters, and my data processing and structure solution should probably be okay. Now I'm going to jump to our second example, which is a twin data set, and I'm going to take the second break of the day for Mark to ask you its second poll question of the day. So Mark, if you don't mind going ahead with your second question.
Thank you, Pierre. So now that we've established that a few of you have some samples that are too weak for your sealed tube system, the question is, how often do you go to the synchrotron or use a synchrotron beamline? Never, because I've never had to for my samples. Never, because it's not convenient. Or occasionally I have to because of weak samples. Again, I'll let this run for about a minute or until we have most of the folks voting. Okay, about 10 more seconds and then we'll end this poll. Okay, thanks for your responses. Let me share the results with you. And it looks like more than half of you occasionally have to use the synchrotron because of weak samples.
Okay, yeah, so 53%, that's quite extensive. So this is for most of you, I suppose, are from the small molecule world, and so we expect protein crystallographers to go to the synchrotron all the time. Maybe less so small molecule crystallographers. So you see, this was the point of this question. And there are also 25% of you who don't go because it's not convenient, which we completely understand, but who might go actually if they could. So that's pretty telling, I think. Okay, so. Now, I see someone who says, not only because of weak samples, but we have to catch weak superlattice reflections. Aha, yeah, I didn't think of that, but you're right. When you have an additional component in your diffraction pattern, wherever it comes from, like for instance, superlattice, and this is much weaker than the main component, then going to the synchrotron might be the only way for you to make those weaker reflections show up. And of course, if you've got a superlattice, you've got to have them appear. Good, excellent. All right, so now let's tackle this second data set, which is a non-mirror twin data set. So again, I'm going to play the data set for you as a movie by pushing this button here at the bottom of the interface. And you see that there's nothing apparently wrong with this data set. It looks clean. You can't even see split reflections or anything. So let me go to the lattice wizard, and then I run a pick hunting with the defaults. gathering reflections on all 4 scans of the dataset, and then I do an indexing by pushing the button unit cell finding. And I've got 82% of my reflections indexed, which is a really good number. So at first glance, many people would tell you that, oh, your indexing just worked just fine. Except when if you look at the unit cell parameters, something is weird, because I've got a long unit cell edge of 67 angstroms, which is more like a unit cell edge for protein structure and not for small molecule. And that makes, as a result, for a huge unit cell, especially for a compound that has barely 20 non-hydrogen atoms. So something is a bit fishy there, and of course, then you want to look at your reciprocal space. And the lesson here is that even if you have a high percentage of reflections indexed, you should always, always, always look at your diffraction pattern in the reciprocal space. You will see things in the reciprocal space that you can't see otherwise. So I click on the eWorld Explorer button, and that's what everything looks like. Let me increase the size of the reflections so you see better what I will be about to show right now. To increase the size of the reflections, I go to the top, another option, another button at the top of the interface, the one that has a wrench and that says GUI settings. So I click on it and select F of I. That will allow me to display the reflections according to their intensity. And now the size of those circles is proportional to the intensity of the reflections. So the B axis is the one that is the long one, 67 angstroms. So on that display, B star is the vertical axis. So you see that along the vertical axis, we have most of the reflections coinciding with the lattice points, thus the high percentage of reflections indexed. However, lots of lattice points are left empty, and that is wrong for indexing. I mean, this cannot be a correct indexing. You shouldn't have so many lattice points left unoccupied by reflections. Now, the thing is that if you project that whole pattern onto the left-hand side axis here, or another way of saying that is that if you collapse the entire diffraction pattern on top of the lattice, okay? So basically bringing all these outside reflections on top of the lattice. I can do that by going to another option at the top of the interface here and opening the pull-down menu near the button that currently says ortho, and then I select collapse to lattice range. So what allows me to bring all the reflections within the area of the lattice, okay? And you see that when I do that, indeed, all the lattice points, or most of the lattice points now are occupied by reflection. And that's why the program got confused, basically, and thought it had to have a lattice point at each one of these locations, and therefore the long 67 angstroms unit cell edge. But this is just display a gimmick, right? This is not real. The real diffraction pattern looks like that, and in that case, lots of lattice points are being left empty. So something is not right here in our indexing. You see also on the intensity histogram along B star that we have a wide, badly shaped reflections at the lattice points, suggesting again that part of the indexing doesn't seem totally right. So now basically this is the reason why CrysAlisPro gets confused here, is because we have a non-mirror hydral twin dataset. And the game for me now will be to rotate around again that diffraction pattern until I've got an orientation that shows intertwined rows of reflections, okay? So to do that, I'm going to remove the lattice from the display by pushing this button here that shows the lattice, so that we're not being distracted by the lattice. And I will go back to showing the reflections as dots. So I'm going back to the GUI settings feature, and then I select again 3, which will display the reflections with a dot, basically with a scale factor of 3. Okay. And so again, with the left mouse, by clicking and dragging, I'm going to rotate around until I see intertwined rows of reflections. So I can rotate around with the left mouse. I want to point you also to another option at the top, again, at the top of the interface, the one that says here, find views. So beside it, you have a scroll bar with a lot of little ticks, and each one of these ticks represents a preferred orientation of the reciprocal space. So with the left mouse, if I click on this bar here and slowly slide it to the left, one by one, so you see I've got a different orientation of the reciprocal space. So you're welcome to use that to see if one of those orientations might actually show you exactly what you want to see, meaning intertwined rows of reflections. So if I keep going, here is one, for instance, that illustrates exactly what I wanted to see. There are vertical rows of reflections here and oblique ones, okay? So now I can take my left mouse and rotate around a little bit more to see if I can align these rows a little bit better. So here I've got it even better aligned. I mean, the oblique rows of reflections are even better aligned. So this is what I meant when I said that I was looking for an orientation that would show me intertwined rows of reflections. So you have clearly two diffraction patterns here. Those rows of reflections crossing each other can never happen if you have a proper single crystal. Okay, whereas here we have two diffraction patterns because we have two components, and I'm getting ready to apply the Lattice-It feature to that view again. Here we're going to take the last break of our webinar, so Mark can ask you one last question for the day.
Okay, so our last question is, have you ever used a rotating anode for data collection on small molecule samples? Yes, I've used one on my occasional weak samples. No, because I never had to for my samples so far. Or no, because we do not have one, but I'm open to using one. Getting nice responses on all these polls. Thank you very much for responding to the polls. Got about 73% of people voting, up to around 77% now. Let it go a little bit longer. Okay, so we're going to end the poll right about now, and I will share the results with you. So we had a little more, I think was than half of people are using the Synchrotron. A little more than half of you have not used a rotating anode because you don't have one. I'll give it back to you, Pierre.
Yeah, good, excellent, yeah, good poll again. It's true that we are seeing more and more small molecule crystallographers also at least inquiring about rotating anodes as people come across weaker samples and maybe even more funky samples, and getting stronger data is always useful in those cases. Okay, so last little sprint here for our webinar, last section. I'm getting ready to apply the Lattice-It feature on that view of the reciprocal space. So again, I'm going to expand the Lattice-It tab and enable the Lattice-It feature by checking the box that corresponds to it. And then I've got these lines following my cursor again. And what I'm doing here is I'm aligning my cursor to the vertical rows, for instance. Left click on the mouse and to freeze the view. And I've got already so a first batch of green reflections ready to be moved to a different group. So I'm going to move them here to group number 2. Let's see what we've got so far. I'm removing group number 2 from the display by unchecking the corresponding box here, and I disable the Lattice-It feature. So here we kept our vertical rows, but we still have reflections from the oblique rows. So why is that? All right, so let me do it again. I'm re-enabling the Lattice-It feature here and aligning my cursor again along the vertical rows and freezing the view. So here what I want you to see is that we have indeed our rows of reflections, those that I will say are fully populated with reflections, properly selected within those bars. However, the next fully populated bar or row of reflections is all the way here, okay? That one. And in between, we have, at the moment, 3 intermediate rows. But you see that these 3 intermediate rows contain very few reflections. It's just that in this orientation, those few reflections happen to be aligned as well. And the program thinks as a result that these are legitimate rows and selects them and selects those reflections within the rows. But again, I know as a crystallographer, I know that this is not correct, that the rows of reflections or the reflections that belong to the first component of my diffraction pattern are those that are fully populated, this one here and that one there. So I need to get rid of these three intermediate rows. And to do that, I will basically increase the distance or the period in between consecutive rows. And to do that, I will move to the right-hand side panel, and I'm gonna use these buttons here for the period between rows. So on the left-hand side, or the left pointing arrow will make the distance between the rows smaller, and the right pointing arrow will increase the distance between rows, and that's what I'm going to do here. Okay, so here we go. I'm clicking on that right pointing arrow button once already there, and you see that all the rows have shifted. So by increasing the period here, it amounts to me grabbing the pattern of rows on the left and on the right and pulling on it. Okay, so let me click on that button once more. And now you see that we've made progress already. That row of that fully populated row is selected by a bar. This one also, and in between we have only two left and no longer three like before. So we are on the right path. I'm just gonna keep clicking on that button. Here I've got that row selected and that row selected, only one intermediate one. And then I keep going, increasing the period in between rows, and keep going some more. And there it is. Now I've got that all the fully populated rows of reflections fully, properly selected, and nothing in between. So you see also that the bars have become a little bit larger, so I can certainly decrease their width by clicking the left pointing arrow button here to make those bars a bit thinner. And now I've got a second batch of green reflections ready to be moved into a different group again. Now, it is very important that you move that second batch of reflections into the same group as I did for the first batch of reflections, because all those reflections most likely belong to the same pattern, to the same component, and therefore they must be put into the same group so that you can then index them together thereafter. Okay. So again, I'm pushing the button move selected to, and I keep group 2 here. Now I remove everything that is in group 2 now from the display, and I disable the Lattice-It feature. And that's what I'm left with on my from my diffraction pattern. So now all I have left to do is index that diffraction pattern from the first component, and then I will index the reflections from the second component separately. So to index these reflections, I'm going back to the Crystal tab by expanding it again, and then I left click on the blue link that says Lattice. And here I'm choosing the first option that says auto unit cell finding in shown peaks, because the peaks that are shown right now are only the peaks from the first component, the first group. So I click on that. And now CrysAlisPro came up with a new set of unit cell parameters of 11, 12, and 9. No trace of that 67 angstroms unit cell parameter again. Okay. So now I can display again the lattice from that button at the top here, and display the whole view along one of the reciprocal space axes. Okay. And now, so as I did all that, CrysAlisPro automatically brought back into the display the group number 2, but I don't need them for now. So let me remove that. So I've got now fewer reflections, that I'm gonna make them bigger again so that you guys can see better. Once more, I go to the GUI settings button at the top and select F of I again. All right, so that's what I've got now along A star, B star, and C star. And you see that now we've got all the reflections indexed or coinciding with the lattice points, and most of the lattice points occupied by reflections. On the right-hand side, on the intensity histogram, you see that now we have strong and sharp reflections at the lattice points. So again, the very fact that these reflections are now so sharp is because we are predicting exactly where their centroid is. So everything looks good at this moment. I still have to index the second pattern, and that's going to be very easy. Since this is a twin, or actually could be a multi-crystal, but since this is a second pattern, I'm going to activate the twin multi-crystal feature here by left-clicking on it. And now I'm going down the list a little, and I say find next component in wrong peaks. Wrong here stands for unindexed. So if I click on that, then CrysAlisPro find a second component whose unit cell parameters are basically the same as the unit cell parameters for the first component within error. And now I've got only 4% of the reflections unindexed. So the first lattice indexed 58% of the reflections, and the second lattice indexed 37%. And now only 4% remain unindexed. The twin law is a 180 degrees rotation along this reciprocal space direction. And that's the end here. I will remove the reflections from the display to better show you the two lattices. And these are the reflections from the first component, and now the reflections from the second component. Okay, so now I've successfully indexed separately the diffraction pattern from both these components. I'm ready to process the data set. To do that, I would get out of the reciprocal space viewer by pushing on this cross button, close the lattice wizard, and then go to Start Stop, and then data reduction with options. I'm going to stop here because processing the dataset is not the point of this webinar, but I will still point to one thing, is that on the step 1 of the data integration dialog, that box here has been automatically checked by CrysAlisPro, and that's what will prompt CrysAlisPro to integrate the dataset as a two-twin component. And that was done automatically by CrysAlisPro because obviously it knows what we just did in the lattice wizard, that we indexed the diffraction pattern as the two-twin component. And at this point, I'm ready to go ahead with data processing, and there shouldn't be any problem after that. Okay, okay, I'm gonna stop here. Thank you all for your attention, and we still have some time if you want to answer some of your questions.
Thank you, Pierre. I would just like to take a moment to address a comment that came in. Really nice webinar. Would be easier to research the peaks and re-index using twin mode from the beginning.
So this in this particular case, again, so CrysAlisPro, I think, catches the proper twinning sometimes, but not always. Usually it locks onto that 12, 67, 12 unit cell parameters I got at the beginning. So I find this is just more convenient to go in there manually and separate these diffraction patterns myself.
Yeah, and I guess the point was to show what to do when the automatic twinning doesn't get you the answer that you need.
Correct. It's just like for the IC dataset, my first example, it's not like I needed to use the Lattice-It feature on that dataset. It was just the best dataset, or the worst, so to speak, dataset I had to show you that feature today.
Great. I don't see any other questions coming in. So if you don't have any other questions.
Just one thing, Mark, maybe let me write my email address here in the chat window, and I will leave that so you guys can write it down or take a screenshot of it or something, and basically write to me in an email later on if you think of something to ask. So please don't hesitate to write to me at that email address. Thank you, Mark. Oh, I see another comment. It will be nice to integrate in index incommensurate orders. Is there something there for that? The answer is yes. So I can show you, of course, I don't have the data set ready here to show you, and we are running out of time anyway. But if you, for a data set, if you go again to the eWorld Explorer, okay, you see that the same way that I had a twin multi-crystal feature, just underneath it Lattice-It, there's an activate incommensurate structure or feature as well. Okay, so this is the feature that you use, and an additional dialog will open up for you to enter the value of the Q vectors that you see that you think are best. And once you enter those Q values, you can refine the cell including the Q vectors. And then once you get out of it, so again, this is basically all you need to do in the reciprocal space viewer, and everything is done in there. And once you've done that, and you go to your data reduction dialog by going to start, stop, and data reduction with options, these feature here that is completely grayed out says incommensurate structures. This will be automatically enabled if you index your diffraction pattern with the incommensurate structure enabled. And so at this point, you just go on with processing the data set with the proper Q vectors, and CrysAlisPro will generate for you the proper reflection file. Now, that's where we stop though. Then you have to take this reflection file to the program YANA, which we don't have anything to do, which you can't find here. And CrysAlisPro does not include that program. It just provides you the reflection file with, so that you can take it and go to YANA and try to solve your structure. Okay, I hope I answered that question properly. Anything else, Mark?
No, it looks like we had no other questions.
Good, excellent. So I guess we'll call it a day then. Thank you very much for your attention, and don't hesitate to write to me if you have any more questions coming up later. All right, bye-bye everybody.
Bye-bye.